Hello. This will be a demonstration of Proposition 33 from Book 7 of Euclid's Elements, which tells us, given as many numbers as we please, to find the least numbers which have the same ratio with them. How we would put this in sort of modern terminology is to reduce any ratio to simplest terms. That's just how we would say it nowadays. What we're given are three numbers, A, B, and C. Shouldn't be surprising that we're given three. This is the simplest non-trivial case. We've seen this before, so shouldn't be shocking. What we're going to do is we're going to find the least numbers which have the same ratio with A, B, and C. Now, either our three given numbers, A, B, and C, are either prime to each other or they're not prime to each other. If they are prime to each other, then we know by Proposition 721 that they are the least of those which have that ratio, which means we don't actually have to do anything if they are prime to each other. If, however, they are not prime to each other, what we're going to do is we're going to find their greatest common measure. We're going to call that D. So D is the greatest common measure of A, B, and C. We can do this, or we can find D, rather, by Proposition 7.3. Then next, we're going to create three numbers, E, F, and G, such that there are as many units in E, there are as many units in E as there are D's in A, there are as many units in F as there are D's in B, and there are as many units in G as there are D's in C. So that's how we're going to create our three numbers, E, F, and G. Now, because, therefore, the unit measures E, F, and G the same number of times that the number D measures the numbers A, B, and C, respectively, of course, we can then say by Proposition 7.15 that the unit measures the number D the same number of times that our numbers E, F, and G measure the numbers A, B, and C. So there are as many units in D as there are E's in A, there are as many units in D as there are F's in B, and there are as many units in D as there are G's in C. And because this is the case, that E measures A the same number of times that F measures B, which is the same number of times that G measures C, for all of those measure the same number of times that the unit measures D, we can then say, just by the definition of proportionality, that our three numbers, E, F, and G, are in the same ratio as A, B, and C. Now, next what we want to prove is that E, F, and G are the least numbers which have the same ratio as A, B, and C. What we're going to do is we're going to do this by a reductio, say that they are not the least numbers which have the same ratio as A, B, and C. If they're not, then there's going to be three other numbers which are less than E, F, and G, which have the same ratio as A, B, and C. And we're going to just create those numbers, because if we assume that they exist, we're just going to say that we have them. So we're going to have our three numbers, H, K, and L, which are the least numbers which have the same ratio as A, B, and C. So that because they have the same ratio as them, the number H measures the number A the same number of times that the number K measures the number B, and the number L measures the number C. That's, again, just by definition of proportionality. And finally, we're going to make the number M such that there are as many units in M as there are H's in A, as there are K's in B, as there are L's in C. So we're just going to create this number M. Now, because, therefore, the unit measures M the same number of times that H measures A, right, we made M such that that's the case, we can then say, again by Proposition 7.15, that the unit measures H the same number of times that M measures A. Now, for the exact same reason, we can say that the unit measures K and L the same number of times that M measures B and C, respectively. And what that tells us is that our number M is a common measure to A, B, and C. Next, because the number H measures the number A the same number of times that our unit measures the number M, right, again, we made M in that way, we can then say by the definition of just multiplication that the number H times the number M measures, or equals, the number A, I should say. So H times M has made A. But again, because the unit measures E the same number of times that D measures A, right, we established that, or at least that's how we made E in our second step, we can also say, again by the definition of multiplication, which I believe is definition 7.15, that E times D also makes A. So that we have two products of two numbers that make the same number. So combination 1, they're equal to each other. So h times m, or I should say e times d, is equal to h times m. And we can then say, by proposition 720, we can convert this statement about products into a statement about proportionality and say that because e times d is equal to h times m, we can say that e is to h just as m is to d. Now, remember in step 4, we made the number h less than the number e. So the number e is greater than the number h, which then means simply by a property of numbers that because e is to h just as m is to d, and e is greater than h, m has to be greater than d. So that because the number m measures our three numbers a, b, and c, so it's a common measure, and it's also greater than d, d therefore cannot be the greatest common measure of a, b, and c, because there is a common measure which is greater than it. But this is contrary to just how we constructed the number d. In our second step, we just made the number d as the greatest common measure of a, b, and c. And supposedly, we found another common measure of a, b, and c, which is greater than the greatest common measure. That doesn't even make sense. So what we arrive at finally is that because if we assume that e, f, and g are not the least numbers which have the same ratio as a, b, and c, we find that d is both the greatest common measure of a, b, and c, and it's not the greatest common measure of a, b, c, which is just impossible. We can then conclude that our three numbers e, f, and g are in fact the least numbers which have the same ratio as a, b, and c. And this is precisely what we set out to construct, as it were. We set out to find the numbers which have the same ratio, or the least numbers which have the same ratio as a, b, and c, and we've just found them in the numbers e, f, and g. So we're done with the proposition, therefore, etc. q, e, f. An example of this proposition would be that if we have three numbers, it doesn't have to be three, by the way, it can be just any number of numbers, right, given as many as we please. So let's say we have three numbers, 12, 30, and 42. What we want to do is reduce this to simplest terms, as it were. We want to find the least numbers which have the same ratio with them. So what we're going to do is we're going to find the greatest common measure, or as we would say nowadays, the greatest common denominator of 12, 30, and 42. We're going to find that to be 6. And we're going to say, okay, how many times does 6 fit inside 12? Well, it fits it inside twice. How many times does 6 fit inside 30? It fits inside 5 times. And how many times does 6 fit inside 42? Well, that's 7 times. So what we found are three numbers, 2, 5, and 7, which have the same ratio as 12, 30, and 42, but they are the least of those which have that ratio. So that's just, that's how this proposition would work with a particular example. That's all I've got to say about this one, so I'll end the video here and move on to proposition 734.